right, hello everybody. So my talk is on how to effectively use both Flink and Pinot to solve certain kinds of problems. My background is more in streaming and big data processing, but we provide consulting services, and for one of our clients, Pinot was exactly the right solution. And in fact, I previously had done a talk called A Tale of Two POCs, where we were talking about trying to solve a problem using Elasticsearch, and it was a complete fail. And then we tried solving that same problem using Pinot, and it was a great success. So this is sort of a continuation of that talk, focused more on the Flink side of things. So as I said, I do consulting. I'm now semi-retired, which means I only work on fun things, which is great. And I'm very active in open source. I'm a member of the Apache Software Foundation. And I started working with big data and Hadoop so long ago, back in 2006. So what's the high-level thing? So Pinot supports some kinds of sort of transformations. Right? You have these minions that we'll get into in more depth, and also the ability to configure your table so that as data is flowing in, you have a table config that specifies transformations to be done on the data. Flink, on the other hand, it's really about these stateful, scalable workflows, typically streaming, though in our case, we are essentially running them as batch. So when do you want to combine the two? So you want to combine the two when it's important for you to offload work from the Pinot cluster. And I'll explain why that becomes important. But one of the issues is, how do you do more work somewhere else besides in your Pinot cluster? Another use case is if you're doing complex transformations, so things that it's hard to do using Pinot, which includes things like natural language processing and some machine learning, things like that, trying to stuff it into Pinot, maybe you could make it work, but Pinot's telling you don't do that because it's hard to do. And lastly, there's an example here of how we can actually help Pinot. We can do things in this Flink workflow that make Pinot perform better. So what's the backstory? So we have a client called AdBeat. And AdBeat collects display advertising for 26 countries. It's millions and millions of ads every day, so it winds up being billions of records over some historical period of like 5 years. They have a dashboard, right? And one of their requirements is a responsive dashboard should be able to update in like a second or so. So we have a limit to our query time. And that's one of the reasons why, when we first implemented this, we did it by pre-computing everything. And then we actually stored it in like Solr, but we could easily then do queries like, in the last 90 days, what was the ad spend on ads that were flash ads that used the word diet pills? Right? We could answer those questions, but we had to pre-compute the answers to all those questions in the batch processing, and that became intractable eventually as the size of the data grew and the number of dimensions kept increasing. You wind up with a combinatorial explosion. So we wound up saying, well, let's try Elasticsearch. No pre-compute, too slow, because you have billions of records, and if you have to iterate over billions of records to get an answer, you just can't do it in a second. It's just impossible. Pinot, thus, was a great solution where we could leverage StarTrees to sort of do pre-aggregations on things, and it gave us the ability to support ad hoc queries versus having to pre-compute everything in advance. So it gave us a lot more flexibility. So this is an example of a dashboard. You're like, well, show me ads in the last 180 days. And I'm looking at what I've got here that mention real-time analytics and sort them by ad spend. Right? So this is the kind of service that AdBeat provides to its customers. So this is what we need. This is a slice of a workflow where we're updating the main Pinot table. And up above here, and you'll see a bigger view of it later, is a whole bunch of data sources, like traffic and actual images. And we are doing a bunch of natural language processing, which involves a whole bunch of joins and some complex text analysis that we'll talk about. And we're doing some machine learning, which is actually about using fast text to calculate semantic vectors, feature vectors, and using those then to be able to say which ads are sort of roughly similar to each other, regardless of the text that's in it. So what's the semantic similarity? And here's like, if you turn your head 90 degrees, you can see the more full workflow. It didn't fit on a page. The green things on the left are sources. The green things on the right are the sinks. Right? We're writing to two different Pinot tables. We're generating two different Pinot tables. Everything in yellow is a join. All the things in white are like filters and maps, flat maps, process functions. Those are all things that Flink supports. So this is kind of what we kind of knew we needed. What did we get from Pinot? Could we leverage Pinot as much as possible? So Pinot has this thing called minions, right? These are things that you can schedule, you can parallelize, you can retry as tasks, right? That are running in separate nodes in your cluster, right? And there was a talk previously about where minions were now and where they're going, and they've gotten a lot better since we looked at Pinot a year and a half ago. And typically how Pinot uses minions, or how people use minions for Pinot, is on data ingestion, like you're reading data from different places, and on segment management, like doing roll-ups, right? Those are examples of tasks that are really well-fitted to minions. The other thing that you can do is that you can configure your table to do transformations as the data is coming in. And typically, this is things like, I'm renaming columns, I'm flattening data, like I've got some JSON and I want to flatten it out. So simple transformations, row by row, as data is coming in. However, it's only for real-time ingestion. And in our particular use case, we have a batch job. We're using Flink to efficiently build segments that then we deploy on our Pinot cluster. And that is sort of the most efficient way to get data into Pinot. I mean, it's got obviously much higher latency, but it is the most efficient way to sort of get your data into your Pinot cluster. So where did that workflow that you saw, that giant directed acyclic graph, where did it come from? It was based on the requirements. What are the client requirements? So one of them is we want to do text-based filtering in 16 languages. What that means is we had to do it-yourself text search in Pinot. The reason why is, for those 16 languages, every one of them has a different analysis chain in Lucene. Like the way you do stemming on words is different if it's for English than if it's for like Dutch, than if it's for like, Japanese doesn't have stemming, but even tokenization, like with Japanese tokenization, it's very different. You have to do a morphological analysis to try and split things into words because there's no spaces. So Pinot didn't support that, and Pinot still doesn't support it. Pinot, a year and a half ago, had these text indices that were based on Lucene. Since then, they've come up with a more efficient implementation called native indices, where they sort of build it as an actual type of index inside of Pinot versus like a sidecar. But it's only for English. So we did do-it-yourself text search by doing the text analysis in the Flink workflow. We actually stuffed the Lucene analysis chain into operators in our Flink workflow, where we would normalize the text, we'd split the text up. Right, so we're doing that all in the Flink workflow. And then what we do is we add a multi-valued string column to our table that has the results of that tokenization and normalization. So what happens is when somebody does a query in the UI, they make a call from the UI layer to a service running that does the exact same normalization and tokenization as a Java service. So they get back a set of terms that they're going to use in their Pinot query. Why is that important? Well, one of the things we do is we create shingles for the text you give us. So if you said, I've got fast text search exclamation point, what we would generate are values that are going to go into this multi-value string column that are fast, fast text, text, text search, and search. All right, so we generate 2 grams. The reason we do the fast text is because we don't store positional data. We don't have positional data in that multi-value column. So we don't know the ordering of the terms. So if we didn't do these shingles that are like 2 words, then we would have a lot more false positives where things match when we're sort of doing a phrase query, but the words are in different locations in the text, right? But positional data is super expensive. Like if you look at a typical Lucene index, it's like most of the data in the Lucene index is positional data. So we say, you know what, we're going to accept some false positives and have a lot less data storage requirements, and we don't need to store positional data. So we did that, and then we got some, it was interesting, we got the unexpected side effects, right, were actually in most ways positive. So there were 2 of them. One was, because we were doing this analysis in Flink, in this scalable workflow, we were removing that work from the Pinot cluster. Like some kinds of analysis, like I mentioned Japanese, is super computationally expensive. So instead of requiring that happen in the Pinot cluster, we're putting it into the Flink workflow. So we're shifting that work. And the other thing is, not having positional data wound up more often than not being a win versus a loss. Like it made it sort of a fuzzy match. So search text faster also would also match faster text search. And again, there's a little bit of the details in how we build the query, but this winds up being a match. So we wound up getting, sometimes lower precision, but we wound up getting better recall. We wound up finding hits that the user actually was interested in where we wouldn't have if we were doing an actual explicit phrase query. So another requirement is fast sorted aggregation across billions of records. So here's a query. Often, almost always, there's an initial filter by country, which helps, except if the country's US, that's like 80% of the data. So it hasn't helped us a lot. And now, this is the interesting one. We group by ad hash, which is like a unique identifier for each ad, right? And what we want to do is we want to sum the ad spend for that hash, for that ad. We want to sort it, descending, and we want to take the top 1,000. Right? So with this query, without StarTrees, it took about 40 seconds to run. And this was, I want to say, 6 very beefy servers in the Pinot cluster. And we had about, I'd say, 20 billion records that matched the US country. So we wanted to make it faster, so we're like, well, we'll throw StarTrees at it, right? StarTree to the rescue. So we did that, but the problem here is that ad hash has super high cardinality, right? So StarTrees are helping reduce the number of sort of essentially values that you have to sum to get an answer. But in our case, it's sort of like on average 4, we could get rid of 4x the record. So it wound up being like 10 seconds to do the query instead of 40, which is better, but it's still an order of magnitude too long. All right, we had to get 10x better performance. And it's all about how do we sum fewer records. So power curve to the rescue. There's always that 80-20 rule, like 80% of the whatever is from 20%. In our case, for these ads, it was a 72 rule. So 70% of the ad spend comes from like 2% of the ads across a number of different sort of dimensions. Like if we're looking at only text ads, if we're looking at only ads from this past month, in general, this holds true. And, another key point here is we never care about find us the ads with the lowest ad spend, right? We're only sorting descending, right? Because nobody cares about the ads that nobody spends money on. And it's a super long tail there. Like you can see here, like you get a whole bunch of ads that have like almost no ad spend, right? So ordering those has not much meaning versus ordering ads by like from the high to the low, that has meaning. So what that meant we could do is we could add a top ads flag. So what we did is we used this KLL float sketch. So if you haven't looked at the Apache Data Sketches project, it's really interesting because it has a lot of approximate algorithm implementations, many of which are streaming, most of which are streaming. So this is a streaming algorithm. You're sending data through it, and it's telling you approximately what the value is if you want to be in like the top 5%, if you want to be 95th percentile or 90th percentile. So we could run all our ads through. We did have to sort of do it multiple times on different dimensions that we cared about, and then we would union those top ad flags together. So if an ad wound up being one of the top, let's just pick a number, 10% by ad spend in December, or it was one of the top ads in November, in either case, we're going to set that top ad flag for all instances of that ad. All right, so we're setting a single flag. The interesting thing here is it's OK if we overflag stuff. If we flag ads that shouldn't really have been the top ad for a given sort of dimension, it just means we're looking at a little bit more data than we should have when we're trying to calculate those top 1,000. We just don't want to underflag, right? We don't want to miss ads. And then we add that flag as one of the dimensions in the StarTree. So now we can do a query using StarTrees where we say, and it's a top ad for wherever it's appropriate, wherever we're sorting in descending order by ad spend. And so now our query time went to 300 milliseconds. All right, so that was from 10 seconds to 300 milliseconds, like a 30x or more win. Great. There is an issue, of course, where if you are trying to do a query on some dimension that we didn't use to figure out if the top ad flag should be set, then you can't reliably use it in your query. So, and you can think about how you could filter the ads you're looking at to the point where it's one ad and it has like 0 ad spend. But that's the answer. So anytime, and you have to code this into the UI layer, the layer that's making the queries, anytime the dimensions aren't ones that we're using for doing that top ad flag, you can't use it, and you take the performance hit. But typically in those cases, the number of ads you're looking at are small enough that it's still fast enough. Right? We only need this case for when we have billions of records, and those cases we handle, like we make sure we set that top ad flag. It'd be great if Pinot did this for us, for members of StarTree, like sitting in the audience, because then we wouldn't have to worry about it, like setting it in our queries or screwing up and not setting it or setting it when we shouldn't, So another baseline requirement is we have these daily updates where every day we get millions of records, and we actually want to sort of reprocess everything from the current month, because there are some things we do that are like calculations for the month. So what does our data processing workflow look like? The first thing we do is we're reading data using Flink from like HDFS and S3, and that's running into our workflow. And our workflow then generates compressed CSV text files as segment files, one file per segment. After we've done that and we store it in HDFS, then we use, Then we use the built-in MapReduce job that's part of Pinot to convert the text files to actual segments that we store in HDFS. Now we could combine those last two steps. We can't actually just directly use the Flink sync that is part of Pinot because of how we carefully partition the data when we're building these segments. Like, it doesn't have enough flexibility for that. But we could extract the code from Pinot that knows how to build a segment from a text file and just bake that into our Flink workflow. So we could skip this step, though it's kind of handy to have the text files around, especially at the beginning, because we could just go look at them. Like, it was really easy to inspect the data and debug what was going on. And it doesn't, on a Flink cluster, like this step right here is minutes, even for very large amounts of data. So, it hasn't been something that we've needed to fix. And then the last step, once we've got all these segments in HDFS, is we do what's called a metadata push. And what's happening there is we are telling Pinot these are URIs to files that are stored in HDFS that either need to be loaded or reloaded. So we're actually doing updates to the current month's segments. And when Pinot gets a metadata push, instead of pulling all that data through the controller, which becomes the bottleneck, it basically just updates its ideal state in Helix. And servers, each of the servers then winds up pulling the files that it needs from HDFS. So it's way more efficient. Does that make sense? All right, so if you're ever dealing with offline generation of segments and it's stored in HDFS or S3, you just want to be using the metadata push. All right, so this is an actual screenshot from the Flink workflow that's running, which represents sort of the physical plan of that logical workflow that I showed you earlier. All right, so this is it actually running. So we're doing a lot of work in Flink, but we're doing it in parallel on a transient cluster because it's a batch job. Right? So even though that's a very complex workflow there, well, first I'm going to tell you about why that workflow looks as complex as it does. So one of the requirements for our client was to reduce sort of their infrastructure complexity. And one of the things they need is auto-completion. Like when the user is typing what text they want to filter in, they want to show options. And what they want to see are the 10 best options for a given set of text they typed in. Right? So they asked, is there a way we can do this with Pinot? So here's what we did. We generate an auto-completion table. What's in that table? We have, it's a table with a keyword, a weight, and n-grams that looks like this. So what this workflow is doing is it's saying, OK, for the mortgage keyword, it has a weight. And then what it has are n-grams, like the leading characters for that word. And it has typically, I think it's 3, 4, and 5 n-grams. All right, so, and we also do it for inner words. So like with mortgage broker, we generate n-grams for both the word mortgage and the word broker. So what happens is when somebody has typed some text in, we make a request for that n-gram ordered by the weight, right? So we query against the n-grams column, ordered by weight, and we get the top 10 results. Why is this complex? Why is this a complex thing? Well, there's two main reasons. One is to calculate that weight, we are combining a bunch of factors. One is the ad spend, so that if an ad, if there's a lot of ads where somebody's spending a lot of money, maybe that's more interesting to the person. But the other thing we do is we have to calculate something called an inverse advertiser frequency. A word like "the" is going to be, every advertiser is going to use that in one of their ads. So if I typed, I don't know, TH, if I had 2-letter n-grams and I typed TH, I wouldn't want to show "the" as an auto-completion thing because it's not significant enough. So what you do is you calculate sort of the percentage of advertisers that use this word and you flip it. So fewer advertisers use this word in an ad, it has a higher score. But to calculate that inverse advertiser frequency, you need to know how many unique advertisers there are. And for each n-gram, how many advertisers have at least one ad that uses that n-gram? So, you can think about how would you do that in a streaming workflow manner? It winds up being complicated. You have to calculate the cardinality of your advertisers, and that becomes input to calculating this ratio at some point in the workflow. And the other thing is, what are the n-grams that we include here? We don't want to include, the other thing here is we need to, we only want to show the top 10 results for any given n-gram. So for MOR, we want to have 10 results. So how do we calculate what are the top 10 results for MOR? We have to find every keyword that has MOR as an n-gram, sum together their weights, and order them by that weight. And we're doing that in the workflow. So again, it winds up being a lot of joins. So it seems hard. It was a little bit tricky. But the end result is they could get rid of what was a separate Solr infrastructure and a separate workflow that was sort of building the index that you could use for auto-completion. And they could just use Pinot. And which means if they're using Pinot, the web UI layer team is just making SQL queries. And they love that, right? Versus having to craft like Solr queries. So the last thing, minimize the Pinot cluster server requirements. So the issue here is we're doing batch processing once a day. And that's a transient cluster. The Pinot cluster, on the other hand, that's 24/7. So they are paying for those servers every hour of every day. So their goal was, how can we have the smallest cluster possible that gives us our SLAs for sort of query time to build the dashboard. So that wound up being all about offloading the work from Pinot. So as we talked about, we try and do as much heavy lifting, as much of the high CPU, complex processing in Flink, where it is transient because it's running once a day. We also, when we build these segments in the Flink workflow, we, at that time, or actually it's in the Hadoop MapReduce job that follows, build all the indices. Like Pinot gives us this option to do sort of lazy or deferred index generation when it gets loaded onto the cluster. But no, like we want to generate as much as we can in our transient scalable workflow, which is offloading the work from Pinot. We also have this thing where, as we talked about, doing the top ads flag meant instead of having, so I mentioned, I think they have 10 servers in their cluster now, but it was at 6, and we needed 10x better performance. So we're like, well, do we need 60 servers to get our 1 second response time here? But instead, because we could use this top ad flag, we could do it with the 6 servers that we had, right? So it's, again, an example of offloading, making your Pinot cluster as small as possible by being able to do that optimization in the Flink workflow. And again, the daily jobs take, I want to say 10 minutes or something, 15 minutes, even if we're processing tens or 20 millions of records for each day. So which is why you can spin up the cluster, you do your work, you build your segments, and then you do the metadata push, and you shut down the cluster, and you're good. So it's a cost savings issue. And because we can use HDFS as this segment deep store, it means we can do a metadata push, which is also more performant. Right? You don't have to have a super beefy controller, the Pinot controller, that all the data is flowing through, because the data is not flowing through the controller. It's just going straight to the servers. So what's the net takeaway? Right? So when should you use Pinot support? So if all you're doing is fixing up your data on a row-by-row basis, then definitely just use your table configuration to do that. Right? There's no reason to have a separate workflow because there's no free lunch. So because we have this Flink workflow that's running separately, obviously we've got Flink code that has to be maintained. And we also need to have Airflow running that's scheduling all these things. So we're adding extra infrastructure in that case versus leveraging what is already there because we have Pinot. Right? So where can you leverage Pinot? In just-time transformations, and also things that minions do well, right? Which is part of it is I need to ingest data from a slightly different format or something. Great, I'll use a minion. Or any kind of segment munging, easily you can do it in a minion. And there's some stuff that we're currently doing in our Flink workflow where eventually it should be done in a minion. We can't do everything, but there's some stuff that we should shift to minions. And then for Flink, complex transformations like we saw, especially when you start talking about machine learning or natural language processing, those are things that often wind up being complex workflows. And the optimizations I was talking about are for the indices, right? Things that you can do to help Pinot do a better job. And the biggest win is if it's batch processing, right? You could use Flink, where you're reading from Kafka, you do all kinds of cool stuff, and then you write results into Kafka, different Kafka topic, that Pinot is pulling from. Right, so in that case, we're not generating offline segments, and it's continuous processing, not batch processing. And there are still use cases where that's valid. But you don't get the win of being able to shut down your Flink cluster after 15 minutes, like every day. So Flink becomes especially interesting, in my mind, for where you can do batch processing. And the third thing is, if by doing processing in Flink you can dramatically reduce the size of your Pinot cluster, then that can be a win in terms of essentially your total cost of ownership, because your 24/7 set of servers can be a lot smaller. All right, that is the end of my presentation. Any questions from anybody? Please, somebody have a question.
Yes, thank you. Can you go into some detail of that top ads flag, like how it's actually implemented? Because first of all, I'm not that familiar with the StarTree index. I assumed it's like a KD tree, which means you've got to index everything to get weights to begin with of some sort? Okay.
I mean, so StarTree is like, it does sort of mini aggregations, mini rollups. So if I have, and it can be multi-dimensional. So if you have more than one dimension in your StarTree, it sort of builds this tree graph of like, here's this, and here's this, and here's this, and then I get a value. It's pre-calculating the aggregations. So if I have like the ad spend, then it could be like for the US, for the month of November, or not the month of November, for text ads, for this particular ad, here's the sum of the ad spend, right? So it's like then you just traverse the tree.
So like ad ID or ad hash ID is one of the dimensions?
In this case, it is, yes.
Okay, so that means that's a high cardinality dimension, which you're mentioning.
So yes.
You have to the granularity of each ad.
Right, so when we didn't do a top ads flag, sometimes there would be like tens of millions of ad hashes underneath a node in the StarTree. And that means when I ask for the sum of that, it's iterating over all. In fact, sometimes it was like 100 million or more. It would be having to iterate over all of those final nodes to sum their spends that have been pre-aggregated, so we didn't win that much. Make sense?
Well, another question, like in the order of dimensions, wouldn't you put the ad hash ID as the first dimension? Because if you put it at the bottom, it's going to be repeated multiple times for similar.
Well, so it turns out that's a good question. It turns out most of the time ads are very transient, and they're only in one country. Like for the dimensions we cared about, there wasn't a lot of duplication, and there was a reason to put it at the bottom, because otherwise what we'd have is a lot of almost empty nodes as we walk through the tree, versus it's a very dense tree until we get to the bottom, and then we have all the ad hashes, if I remember correctly. I mean, this was a year and a half ago.
We can even go offline, but I assume because they're like keywords, and keywords are common. So let's see, there's a keyword that has 1,000, maybe 1 million ad hash IDs, and keyword is one of the top dimensions. And then another one has another 1 million, and there's a bunch.
Yeah, so we don't do it. We don't do that by filtered by keyword. Because once you start filtering by keyword, the number of ads you have winds up being small enough that it's fast without having to rely on the top ads flag, or the StarTree. Yeah.
Okay.
I have a similar question on the top ads flag. Ads is like a very seasonality, right? Can you hear me?
Yeah, sorry, go ahead.
Ads has a lot of seasonality into it. So how are you going to handle the promotion and demotion of an ad being into the top category list?
So how do we, you mean how, like if like this coming month suddenly we have like, right, so.
Flash ads. Flash ads, very short period ads.
Right. So how do we handle the promotion and demotion of them as being a top one? So what we do, one of our dimensions is the month that it occurs in. Right, so that already then segments by time sort of this space that we're doing it. And so when we calculate the top ad flag, it's like on a per month basis, right? And that's why we reprocess the entire month sort of, when we're doing our daily runs. Does that make sense? So like by partitioning by time in a pretty tight, like actually, do we go month or day even? We might go by day. It works out that we can handle very transient ads. Right, we'll set the flag on it if it had a significant spend in either its day or, it's either day, week, or month. I forget what we had to wind up having to do. What we did is so a good question, how do we validate this? So what we did is we had a Pinot cluster without the top ads flag, and we had a Pinot cluster with it, and we'd run queries and see how many in the top N were the same. And we gradually sort of tightened things up and had fewer and fewer ads getting the top ad flag set until we started losing confidence that it would be in the top, in our case, I don't know, 100 was I think our limit that we were using. Does that make sense? So it was a great way to tune the parameters so that we weren't worried about losing valid results. Right.
Hey Ken, great presentation. I just wanted to add, I work for StarTree. We have added auto scaling to minions. So minion is not a fixed infrastructure anymore.
Right.
So depending on the work, it will auto scale up, finish the job, and scale down.
OK. Is that only in StarTree Cloud?
That's a great question.
That might be a pay-to-play option, is what I'm saying.
OK, I'll get back to you on that.
OK.
Yeah, but that capability is there.
Right.
Customers are
Right.
using it.
Right.
Yeah, I'll get back to you on that.
Right. And I should have mentioned with minions, I mean, where it starts to become problematic is if you have an output from one minion has to be the input to another minion. So you start essentially trying to build a job graph. Currently, that's not supported. I think they're planning on supporting it. I kind of feel like then you're re-implementing Flink inside of Pinot. And I'm like, is that really the right thing to do? So I know it extends the reach, and that's always considered a good thing. But I think the very first slide I had is each according to their abilities. That was my tagline. Figure out what each thing is really good at and use it for that thing. And try to avoid abusing a system for something it's not good at.
On the search, how did you handle the typos and the related keywords that Lucene is good at with n-grams?
So we don't really handle typos. I mean, we don't try and auto-correct misspellings. The one thing kind of that happens is we initially do an AND query of everything that gets generated, and then we can turn it, if we don't get enough results, we can turn it into an OR query, so we make it fuzzier. So sometimes two queries happen, just to get a sufficient set of results.
So I've worked in search before, and I see this pattern, right? So you have MapReduce, you have documents that are ingested, you generate the inverted indexes, right?
But in our case, we're not generating an inverted index.
You're not in, yes, and
Right.
so the same thing could be accomplished by inverted indexes with forward indexes for counting. That's the very traditional way of doing it. Why use the StarTree? Why do it this way?
Well, we're not really using StarTree. We're just putting it into Pinot because we want the ability to filter by keyword in Pinot. So when we're making these Pinot queries, we can say, show me all the whatever HTML5 ads that use diet pills that occurred in the last month, sorted by their ad spend. And so we have to do text-based filtering. We're not doing traditional search, which means we don't need the BM25 or TF-IDF scoring for the results. We're not using it to order results. Typically, the ordering is by ad spend or some other metric.
I mean, you could use any kind of scoring mechanism, right?
Right. But in our case, it's not something related to information retrieval sort of technology, right?
But the reason I ask this is, in this case, those indexes are very good at staying in disk and getting pulled into the page cache only when you need it.
Yep.
Whereas,
Same thing for Pinot.
Okay.
Right? Pinot, it's using columnar store for those multi-termed, multi-valued fields, and it's only going to pull in the stuff it needs, and we can have all kinds of optimizations for Bloom filters for values that are there, so we're only we're not having to inspect every block of data that is stored in the Pinot segment. So Pinot segments have a lot in common with doc values from Lucene. Right? Columnar format optimized for efficient lookup, memory mapped, et cetera, et cetera. So it actually works pretty well. The net is, I mean, it works. If it didn't work, then we'd be like, oh, maybe we should be doing something else. But it actually works pretty well. Thank you, everybody.